Okay, this is the mini project supplement for the t-test for means. We have 3 problems here. According to the AAA Foundation for Traffic Safety American Driving Survey, U.S. drivers spend on average 51 minutes behind the wheel each day. Researcher, however, believes this is an overstatement. To investigate, a random sample of 75 drivers were selected. The study revealed that the mean time behind the wheel for the sample of 75 drivers was 46.4 minutes, with a standard deviation of 18.8. Is there convincing evidence that the mean time behind the wheel for all U.S. drivers is less than 51 minutes? And here we're going to use an alpha of 0.01. If an alpha is not stated, similar to what we did with proportions, we're just going to assume 0.05, but here it does state at 0.01. We want to really make sure that if it is different that we get it. Okay, so first off, we're going to state HO and HA. Now remember, just like with proportions, the HO is always the equality, and it's always about the population mean. So here, we know it's not going to contain this sample mean of 46.4. So I can automatically eliminate A through C. It has nothing to do with the sample mean. It's all about that population mean. So all these are equal to 51, so we're good with HO. Now HA, he thinks that this is an overstatement. So he thinks that the actual speed is less than that. So the one that matches that is D. And just like before, do we have evidence for this? Do we even need to run a test? Like if he ran this, or he or she ran this, and we ended up with an average of 52 or 51, we would need to run a test. But we do have some evidence, right? That the mean, our sample mean of 46.4, so the sample mean of 46.4 is indeed less than 51. And the big question is, if I took another sample of 75 drivers, how likely am I to get a sample mean this far away from 51? This far away or more extreme? If indeed the true I keep saying temperature, the true mean speed is 51. So we do have evidence, and now we're going to run our test to see how likely am I to get a 46.4. That does seem fairly far off, around 4 or so, 4 miles per hour, with a standard deviation 18.8, but let's see. Okay, in StatCrunch, we're going to go to stat. It's a t-stat. We always use the t-stat for means, and we have one sample, and we do not have the raw data, we just have the summary data. So our sample mean was 46.4. Sample standard deviation was 18.8. And the sample size was 75. And then we just fill this in. We're comparing this to the population of 51, and don't forget to change this. Okay, I personally like to have a p-value plot. It gives me just another visual like this. So it seems pretty unlikely to have happened by chance, but notice our p-value of 0.0187. It's also here in the table, 0.0187. It's rare, but it's not rare enough, right? It does not go below our threshold of 0.01. And I jumped the gun a little bit. I think I told you t-test. The hard part comes when these are all mixed up, right? I mean, it's pretty easy to know it's a t-test when you're in a section on t-test. They're all going to be t-tests. It does get harder later on when we mix these up. And our conditions, we're assuming that they're met. It says it's a random sample, 10% condition, so we want to make sure that our sample is not too big. Almost never a problem in here. And then it needs to be bigger than 30 or roughly normal, and we're very lenient on the normality here. Really, so long as there isn't extreme skewed. So this is met. Our N is bigger than 30, so we don't even have to look at the graph. And you should have seen that from the chapter summary video and from their textbook reading. Okay, so let me go ahead and just copy and paste those charts in, which you will need to do when you do yours. So there is that one, and you don't have to put the p-value plot, but you certainly can. Okay, so here's our test statistic, -2.12, and the p-value is at 0.0, we'll say 19. Okay, so we're going to fail to reject, right? Even though it's a low p-value, it's not too low. If our alpha was at 0.05, we would reject. But we set this before we even collect our data. So we're going to fail to reject. So because the p-value is bigger than 0.01, we fail to reject. There's not enough evidence, or not convincing evidence, I should say, that the mean time spent behind the wheel is less than 51 minutes. Even though our sample came up with that, that's evidence, but it's not convincing evidence. Because I know that if I took another sample, I could get something that's a little bit bigger. In fact, it's only 2 out of every samples would I get, roughly 2 out of every 100. Would I get a sample this extreme if the true mean were 51 miles per hour? Okay, and I believe on the projects and sometimes on the test, I have these as choices, so just make sure that you're able to pick the right choice. Okay, number 2. Health director of a large company is concerned about the effects of stress on the company's middle-aged male employees. According to the National Center for Health Statistics, the mean systolic blood pressure for males 35 to 44 of age is 124. The health director takes a random sample of 72 male employees in this age group and records their blood pressure. The data have a mean of 126.93, standard deviation of 14.9. Do the data give convincing evidence? This is sort of our word here, right? Convincing evidence that the mean blood pressure for all the employees in that age group differs from the national average, and we're using 0.05 level of significance. So here's the national average at 124. Here's our sample mean at 126.93, about 3 points higher. So do we have evidence? Yes, we do have evidence. The sample mean is different than 124. And I forgot to state HO and HA. So we have HO is the mean equals 124, and HA, the mean does not equal 124. Our conditions are met. We've got a random sample, and often we just have to assume it's random. It's not bigger than 10% of all the employees. We're assuming that. And we have 72, so it's bigger than 30, so that's met. And if you're looking at a sample size around 9, 10, 11, 12, or anything less than 30, you would really need to do a histogram or box plot or dot plot. Okay, so let's go ahead and run our test. So we're going to go stat, t-stat. We have one sample and we have summary data. If you pick the wrong one, it'll be obvious because we don't have it. If you picked the data, and I think number 3 is a data one, you won't have any rows here, any columns to choose. Okay, so our sample mean was 126.93. Standard deviation, 14.9. And we had a total of 72. And we're comparing this to 124, and we're seeing it's a different. So we're leaving it at the not equal to. I like a good p-value plot. So here we go. I can click over here. So I'm getting both tails here. So we got a p-value of 0.0996, or basically 0.1. Here's our sample mean. Here's our t-stat. So you'll copy and paste those over. Okay, so what's our decision? Well, it's not rare enough, right? It is different. It's about 3 points higher, 3 or 4 points higher. Well, I guess just 3 points higher. And that's not far enough away. That was what my gut was going to tell me, but sometimes my gut's wrong. So we're going to fail to reject. There's not enough evidence to conclude. And then I have to look up. There's not convincing evidence that the true mean systolic blood pressure differs from the national average. And let me put that in here. Let's go and run a 95% confidence interval. We often run a confidence interval when there is a difference, but I just want to show you something here, just like we did with the proportions. So let's go and go to options, edit, and go back to 95% confidence interval. Here's our interval from 123.4 to 130.4. And the thing I want you to notice here is that notice that 124 is contained in the interval. So it is a plausible value. So that's another piece of evidence that to reject HO. And this is always consistent with the two-sided test that we have here. When we have the not equal to, if you fail to reject and you run a confidence interval, that parameter, in this case 124, will be in that interval. If it's a one-sided test, it sometimes is not if it's pretty close. Okay, I wanted to give you at least one problem that had a data set. It's recommended students get 8 hours of sleep a night. I believe that my stats class gets less than the recommended hours of sleep per night. To test this, I take a random sample of students in my class, record the number of hours sleep for each, do the data to provide convincing evidence that the stats students get less than 8 hours of sleep per night. Here's my data set, so I'm going to go ahead and open that. And this is an actual data set from one of my classes. Okay, so we have 13 people that participated. I'm going to go to stat, tstat, one sample. Well, first, let me do what the problem is. It says calculate the mean and standard deviation. So let me do that first. I'm jumping the gun. I'm getting too excited about running my t-test. And let's go ahead and run that. And here we go. So our sample mean is 6.8. Standard deviation is 1.25. So what's our HO and HA going to be? So our HO is that the mean, the mu, equals 8. And what about HA? What's the mean? And often, just for my own sanity, I will state what the mu is. This is really for you. It's a good practice to get into. You go ahead and define what our variables represent. So mu is the true mean hours of sleep for stats students. And it probably should say at MTSU. And do we have evidence? Well, yeah, our sample was 6.8, which is definitely less than 8. And the question is, if I took another sample of stat students, how likely is it, if the true mean really is 8, that I get a value this low? A random sample, kind of treat it as a random sample, although it was a pretty convenient sample, just my class. Definitely not more than 10% of all stat students. Now it was less than 30, so let's go ahead and look at a histogram or dot plot or box plot. Okay, so if I do a dot plot, make my dots kind of big. Okay, so it's pretty uniform actually, right? So long as it's not really skewed, I'm going to be okay. The t-test is called a robust test. It can kind of handle departures from normality. And let me do a box plot just to make sure I'm checking my outliers. I like them horizontal. Yeah, so I don't have major outliers. So we are good to go on doing a t-test. So it's going to be stat, t-stat, one sample, and this time we have data. And now I can click on that. And our mean, don't forget to change these, matches up with what we have here on our paper. I get like a good p-value plot and press compute. Let me look at that p-value plot. We're pretty far off here, right? Pretty far away from 0. So we're more than 3 standard deviations away from the mean. We're going to be correcting HO. I can already tell p-value of 0.0025, very low p-value. Okay, so that's really all we need. This screenshot here, and we're definitely going to reject HO. Very low p-value. So p-value is definitely less than alpha. We reject HO down here, D. There is convincing evidence that the population mean sleep time for MTSU stat students is less than 8 hours. And if we want to know sort of, well, about what is it, we could run a confidence interval. That's usually the next natural question. We say it's less than 8 hours. Well, what is it? And if we had one number to decide, we would say it's 6.8, but we know there's sampling variability. I take another sample. I'm not going to get exactly 6.8. So I would create a confidence interval around that. And just to show you, I went ahead and edit, change the confidence interval, press compute. Here's our interval. So we're 95% confident the true mean sleep for MTSU stat students is between about 6 hours and 7.5 hours. Or you could say 6.05 hours and 7.56 hours, however you want to round on that. Okay, so I hope that helps.